So today I'm going to talk about various timelines. We have the AI timeline, we have main events in crypto, we have confidential computing, several techniques, and also law and governance. So I'm going to talk about all of that. It's going to be quite overwhelming because I give a lot of information, but we will skim through it, and I hope you will get a solid view of this whole ecology, if you will. So you all know that bright minds came together, and in 1956 we got a conference and AI was born. Now, we had a continued development, and we already saw some interesting ideas, right? So we had automated reasoning, checkers program, we had ELISA, the first chat program, but there was a lack of progress, and we had to wait a little bit with new impulses coming in the 1979 with reinforcement learning. The recent Turing Award, right, was handed out to the authors, Sutton and Bardo, of this work. We got recurrent neural networks, very important, right, for long-term, short-term memory that we all need in the LLMs, like we need that type of mechanism. And backpropagation got reinvented for AI. Beautiful. However, there was a lack of computing power. So now we really had to wait for the computing power to boost up so that all these beautiful theoretical concepts were able to play out. So then we got convolutional neural networks. Beautiful invention, LeCun, right? We got IBM Deep Blue, beating the world chess champion Garry Kasparov. The first GPU only in 1999, right? We're all working with GPUs, but that's when it happened. Word embeddings and attention by Benjo. Beautiful. We need those concepts. And cloud computing took off, and now we are really getting up to speed. The computing power gets there, and AlexNet is invented, right? A deep convolutional neural network, fantastic, that beats the existing systems by quite a bit. AlphaGo, if you have seen the movie, I was very touched at the time when I was at an ICML conference when they showed it. Unbelievable. Beating the Go master Lee Sedol. Then we had transformer architecture based on attention, revolutionizing natural language processing in 2017, right? And now we get into the modern area, starting 5 years ago with ChatGPT DALL-E bring AI-generated content, right, to the mainstream, and continued development. Autonomous AI systems, AI-assisted medicine, generative models, multimodal AI now, right? We want to have different data formats coming together. Explainable AI is super important because if you have a medical AI assistant interpreting, say, X-ray pictures, you want to have an explanation. You cannot just give your decision. You need to know and understand where that decision comes from. And ethical AI, what about misalignment? And now, just now, right, we have all these foundation models coming into being. And where are we? Well, out of these simple neural network computations, this emerging complex behavior emerges. Unbelievable. It's just based on Bayesian inference, statistical inference, right? And we do not really understand what's happening. We lag behind to some extent, right? Like a lot. So if we design systems or we try new things, it's a heuristic. We experiment, we simulate, and we look at how benchmarks react, right? But you see creation of nonsensical data, we see creation of non-ethical output. Of course, models can be attacked as facility machine learning. I will not talk about that today. But, LLMs cannot really be relied on for decision making. Yeah, you want to use it as intelligence augmentation. For example, with the process mining that we saw yesterday, right? You want to now use that and then in combination with AI, get a fantastic system. Now, today we're going to talk about private sensitive data. So if you're training new models and so forth, well, what can you do about your privacy? So we'll look at a general example, that of federated learning. And in federated learning, the idea was, hey, I do not want to send my raw data to a central server. No, I'm going to send just the gradient updates to the central server, who then aggregates it. And even though you do not send the raw data, it turns out that those gradient informations still leak a lot of your training samples. And you can do membership inference, you can do reconstruction attacks and so forth. So what can we do? And to get there, I'm now going to talk about timelines with respect to confidential computing. But first, a little bit about crypto. Main events also happened after the Second World War. The birth of information theory, very crucial for the development of cryptology. The first CPU came about together with the first wide area packet switch network, together with the concept of symmetric key cryptology, which means that you use a secret key and you encrypt a plain text. With that secret key, you get a ciphertext, and you can use the same secret key to go back, decrypt the ciphertext into the plain text. Then we got a beautiful series of papers that introduced public key cryptography. Fantastic concept. A public key can be used to encrypt data and a secret key to decrypt it. A secret key can be used to produce a digital signature, and a public key can be used to verify the signature. We got the internet. Then we got quantum algorithms. Peter Shor showed that all this beautiful public crypto that we had up to that point can be broken with a quantum computer if it exists. This got broken, the symmetric key standard, key encryption standard, and replaced by the advanced encryption standard. Then we had a whole development also in post-quantum crypto. I'm just telling you this because only now, in 2024, we have NIST standards published so that we can make a transition to practice of new encryption, hash schemes, signature schemes that can resist a quantum computer or an attacker using a quantum computer. That's a 30 years lab, a transition to practice from theory all the way to practice, 30 years, so remember that. So now I'm going to talk about various techniques that we know about in confidential computing. We have secure multi-party computation, and with secure multi-party computation, a beautiful concept, what you can do is you can, with a bunch of parties, you can together evaluate a function, but in such a way that if I give my input to the computation, then another party cannot know anything about my input except for the final output of the function that was generated, plus, of course, the input that this other participant has. So in this picture, for example, party P1 provides X1, gets out Y1. It has those two pieces of information, but cannot derive more information except for the prior belief that it has about the distribution of the other inputs, about those inputs of the other parties, like X2 up to Xn. A fantastic concept, can be used for privacy-preserving data analysis. And also this already started in 1979 with special purpose protocols. That was the introduction. A beautiful concept called oblivious transfer was introduced. In oblivious transfer, a sender is actually transmitting one piece of information out of n pieces to a receiver, but not knowing which piece it sends. So the requester is asking for the piece, but the sender will not figure out which piece it actually reveals to the requester. And the requester cannot find out any other information but the piece that it requested for. A beautiful concept, crucially important. Zero knowledge proofs. Another is it's a philosophical contribution, I would say, because one party can convince another party that some given statement is true, but without conveying any information about the mere fact, right, that the statement's truth. Then we got an improvement in OT, that was really great. Then we had the first, now, two-party computation, secure two-party computation based on coupled circuits. And now we were ready. 1987, fantastic a piece of work that talked about multi-party computation in the way that I just described it. And it's about exactly what I just said, like a sharing of, uh, of inputs together with zero knowledge proofs in order to be able to withstand a malicious participants. And with OT, very important in the first phase to make sure that information is exchanged in certain ways. Now, beyond that, we started to try to make this more practical, right? So we had Sigma protocols by my colleague Ronald Kramer at CWI, with the effect that we got more efficient zero-knowledge proofs. Private information retrieval, I have to just put it on a timeline because it's a simplification of all this, but it's very important for database systems. And you probably have heard about it. But then from 1979 to 2019, 40 years, we have the MPC Alliance. Actually, MPC meets practice. We have several industry pioneers like a whole list. You can go to the website that all use MPC. So is this good? Well, in the federated learning example that I just said, in its pure form, right, then we have many participants offering potentially their gradient updates. And therefore we need highly scalable MPC. Can we do that? Well, for non-constant round MPC, the round complexity, so the number of interactions that we do, is going to scale linearly in the depth of the circuit. That's not practical here, okay? We cannot use that. Constant round MPC. Well, then in that case, it looks good. Nice asymptotics over here in a strong honest majority setting. So that makes sense. It's still a good thing to have. But it requires heavy cryptographic primitives, incurring large computation overheads. And what we need is really a lot more theoretical research to really push MPC into the AI as we know it for distributed learning of models on the training data that we all want to contribute. Of course, right now, what we want to do is we want to maybe scale down the concept of MPC, right? So in practice, unfortunately, this paper got a lot of citations in Crit 10, and I say unfortunately because they completely deviated away from the idea of MPC, which is they introduced a trusted third party. Granted, it's an offline trusted third party that's doing pre-computations, but still, if you assume a trusted third party, why not just use the trusted third party to do your computations to some extent? Why just helping out in the OT phase? So it's not really what we like. It's really a very weak, it's heavy. It's a weak defense, if you will. If the trusted third party cannot be trusted, so to speak, you're done. That makes sense. But you can also say, well, let's say we give a bunch of servers, a small fixed set of servers. We share. So if I participate in this training, so my data is used for creating my local updates. And those local updates I'm sharing among a fixed set of servers, and they will run an MPC protocol together. That's much better. It's still kind of weak, right, to some extent, but it's much better. You need to assume here that those servers to which you outsource this computation do not collude. All right. So now we have other techniques. We have partial homomorphic encryption. That means that if I have an encryption, I can do the following. I can add two ciphertexts, and miraculously, it can be interpreted as a ciphertext of the addition of the plain texts that corresponded to these ciphertexts. So addition and encryption commutes. Functional encryption generalizes public key encryption. The secret key that you use for decryption actually evaluates, if you will, a function, a mathematical function on those inputs, that the plain text that were encrypted. Fully morphic encryption, wow, you can commute both addition, and multiplication. So what you can do is you can perform, evaluate under encryption a Boolean circuit or an arithmetic circuit. What an invention. Since that time, so let's go over some more timelines. So what do we see? Again, RSA was introduced. That was the first partial homomorphic encryption scheme. We got the idea of fully homomorphic encryption, called privacy homomorphisms, already in those days. A lot of work on partial homomorphic encryptions. We got functional encryption introduced, properly defined, and then even solved. In 2013, actually a fully functional encryption scheme was proposed that can evaluate arbitrary mathematical functions. And then Greg Gentry actually solved fully homomorphic encryption, the holy grail of cryptography in those days. So then we had a lot of other schemes that popped up, and we merged, we evolved toward a situation where we now have, say, good schemes, and we even built fully homomorphic encryption hardware accelerators. In 2021, F1 actually evaluated a shallow neural network of about 7 layers on encrypted weights. Beautiful. We also have multi-key fully homomorphic encryption, meaning that multiple participants can encrypt the data with their own keys, but in the end, if you want to do decryption, they need to bring in all their secret keys together in order to make the decryption work. So that needs an interactive MPC protocol, and you cannot get away with a non-interactive online phase. All right. You may not have heard of this at all because this is pretty recent, but we have indistinguishability obfuscation, an even stronger primitive than everything that I have talked about before. It's about obfuscating any two programs that compute the same mathematical function and results in programs that cannot be distinguished from each other. Together with a one-way hash function, it implies pretty much everything. Now, I/O was proposed. A candidate was constructed and later broken. Then I/O can be derived from functional encryption. And we had a scheme, right? But that scheme actually does not work because you have one extra demand requirement, which is that, in the case of long outputs, you also, want to have this sublinearity in the circuit size type of dependency. And actually, this type of construction from 2013 cannot be adapted in that way. But then we had a solution in 2021. Now, this is a very strong primitive, and you can imagine that public key encryption, all right, you do not need that much computation, you do not need that much storage or communication. Then you go to functional encryption. It's already a lot more work. Then you go to fully homomorphic encryption. You need to do a lot more work, more plain text to ciphertext expansion. And now you have I/O. That's even a huge amount of memory requirement, plus a lot of computation. So it's not practical at all. Who knows, maybe in many decades we'll see a transfer to practice. I'm not sure. A third technique, right? So beyond MPC and fully homomorphic encryption, right? We have secure processor architectures. They establish a trusted execution environment. We have Intel SGX as an example. You can do computation in a RAM model. Very efficient, goes beyond just Boolean circuit evaluation, right? You can have loops and stuff like that. So what's that timeline? So we have an IBM 4758 as the first secure coprocessor. In academia, we had XOM. That was not secure because it needed memory integrity checking mechanism and freshness proofs. That's what we did. And we also we also had the concept essentially of secure enclaves. That's what we get that Intel Test of Time Award for. And then we had Bastion from Princeton. We had on the industry side a lot of work, TPM, Trust Platform Module. We got Intel, AMD stepping in, IBM and ARM. Then we had a split in two kinds of confidential computing. One was, hey, the physical attacker has, so you actually have a physical attacker close to the processor, and has access to the data bus. And so you have untrusted DRAM. While now in practice with cloud computing and stuff like that, right? We now in practice focus on the remote attacker. The remote attacker is one who can co-locate a computational thread on your process, on say the processor in the cloud, and you cannot trust the operating system. So on the top branch, we had a great also transition to practice actually from theory of Oblivious RAM in 26 years to Patho RAM, and we were able to solve that. But Intel SGX, of course, went this route. That's the one, the way to go for it. We had a lot of academic contributions, and again, industrial contribution with the first confidential CPU in 2022 by NVIDIA. However, we have speculative execution attacks, right, on industry processors. You may have heard about those. So the problem is that if you do resource sharing, so you context switch in and out, right, different processing threads, they do share all kinds of buffers. For example, speculation buffer, other buffers too, table lookup buffer, blah, 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 all kinds of stuff. The caches, of course, in the system and so forth. And this leads to side channel attacks. And we have a continuous understanding now, starting in 2018, that this is a serious problem. All right, so where are we? Well, we do have an academic proof of concept for how to do all of this. We can do confidential computing in terms of TEEs in a remote adversarial setting. But in industry, with legacy code and practical requirements, well, we lag behind. We can guarantee virtual execution, a verifiable execution environment, though, because that allows us to get to essentially verify that my computation has happened on that particular machine with my code and my inputs in combination with serial knowledge proofs. And this can potentially be combined with NPC. So now we have talked about TEE and NPC, and that's how you protect information leading to the final model. Differential privacy is about protecting what can be learned about the computed output. All right, so that's the final model. So in differential privacy, the idea is that my gradients that I compute, I will clip them, I will add Gaussian noise. So if I have a certain sample that I want to keep private, I do not know a priori which one that is though, but I want to get this privacy guarantee, then essentially whether that gradient is, that special distinguishing gradient is used or not in my batch STD approach, creates two distributions. So we can transform it into hypothesis testing. And that's what happened throughout all the years of this development. So we started off with epsilon DP, epsilon delta DP. You may have heard about those, they're very popular. Divergence-based DPs. And then the holy grail, 2021 in this field, I would say, is Gaussian DP and FDP, because this allows you to have a tight analysis with respect to the worst case adversary that we always use in these proofs in modern cryptography. And what does it do? It's doing exactly that hypothesis testing. So if I use my differentiating sample in my gradient batch that I've computed, and I want to transmit it over to the aggregating server, right, the average of the batch, then I will get, say, this distribution because of the Gaussian noise that I add to it. It's multidimensional, that's true, but we can project down on one dimension, so you get this type of picture. And this is if the distinguishing sample is not used. So clearly, if I can distinguish these two distributions, that's the hypothesis testing problem, I can get a good estimate of whether that the special distinguishing sample was used or not. So we get the membership attack, for example. So what we do is we want to create a plot, a trade-off function between the false negatives and the false positives, the best that you can achieve. And it's pretty clear that this noise needs to be very large in order to have those two curves be overlapping so that you cannot see too much, that you cannot do a good hypothesis testing. Unfortunately, we showed that with the given parameters, the sigma, the Gaussian noise amplifier is actually super large if you want to have reasonable privacy bounds. Now, in machine learning, we see all kinds of results where papers publish, oh, we got a differential privacy guarantee with epsilon equals to 1. Is that good? No. 2, even worse. 8, 10. You should think about it, what you really prove. The privacy guarantee that you prove, for example, with an epsilon equals to 2, really means that one hypothesis is 8 times more likely to be true than the other one. Oh, so with a few observations, I can actually I can do a successful attack, right? It's not a good, solid differential privacy guarantee. It's a beautiful proof, beautiful theory, but you want the epsilon to be really small. Is a half good? Also not good. Is 0.15 on the next slide? Is that good? Also not fine, I'll show you. It needs to be really small, but if you do that, then the sigma needs to be so large. It's not possible. These gradients that you have, they will actually, with the noise, the signs will individually flip arbitrarily in this vector. Terrible. Our training is not robust for deep neural networks in that sense. So here's a picture, and we see essentially the false negatives, false positive plot. And the diagonal line is random guessing, so it's ideal security. But even visually, I can already see that I can break this privacy guarantee with an epsilon 0.15. All right, then we go to PAC privacy. Maybe that can bring the utility privacy gap together. It's very nice. I will just demonstrate this slide because that's really the core. The idea is that I'm first going to have a batch of gradients that I compute. I will look at this geometrical distribution of that, so I have an estimate. That leads me to understand the entropy, and I can create a noise distribution fitting that geometry. Then I do my actual sampling. I compute the average gradient, and I add noise from that distribution that I just computed. So this is instance-based crypto. Very different from what we had up to that time. So it may actually change the way we're thinking in modern crypto. It's very interesting. However, we don't know where we are with that. It's still ongoing. So for now, heuristic, non-rigorous approaches. Of course, you need to benchmark against state-of-the-art membership and reconstruction attacks. You may use adversarial regulation, knowledge distillation, query rate limiting and confidence score masking, data level mitigations, and so forth. So we're not there yet for differential privacy and its derivatives. Now about governance. We had the data protection derivative, the directive, HIPAA, beautiful things that happened, right? EPD, GDPR with its which also served as a model for the CCPA and the LGPD. The problem is that we have the political trilemma, which holds that democracy and national sovereignty and global economic integration are mutually incompatible. So if you have very strong laws or requirements, you may not get the investments from foreign investors for your AI. So how do you do that with the Artificial Intelligence Act? Well, you follow suit with what GDPR is doing, which is you have a risk-based cybersecurity requirements. So there's no prescribed specific cybersecurity measures, and you do not have to adhere to a standard. You only need to make your own risk assessment and do something sensible accordingly. So beyond GDPR, the AI Act will consider regular data, personal data that's not subject to GDPR. Like GDPR, it will actually implement a risk management system, data governance measure, and appropriate human oversight. And I like to mention that you have the right to get an explanation of a decision made by a high-risk AI system. Very important, we discussed that before. This is my concluding slide. So we have a bunch of timelines, right? So we have the birth of AI with an explosion, extreme in the last couple of years. We have MPC with a 40 years transition to practice. Fully morphic encryption is still ongoing in its transition to practice. TEE has stalled somewhat, I would say, but we have lots of transition to practice, but we still need to do more. And it needs work to get this applied to AI. But we need to include output privacy heuristics, because differential privacy is not where it is. And in the meantime, we have the AI Act that was created. So thank you so much. I'd like to advertise also for the CWI lectures that we have on November the 20th, if you happen to be here. And you may see these two names, Srini Devadas and Ingrid Verbouwheden. They are actually on the slides. I referenced their papers. They're two of the main big thinkers that contributed to the confidential computing timeline. So thank you so much.
Marten van Dijk. Any questions? Anything you would like to know about privacy and machine learning? Once again, I would like to know who you are and how can we help you?
Hello, my name is Rahul Nambani and I'm a medical student and I'm based on the Italy and the Greece, like I'm doing industrial PhD. First of all, thank you for the wonderful presentation. So basically my background is more the computer vision, but now I'm doing the PhD based on the privacy preserving anonymization in the agricultural sector. So like I'm currently using the federated learning for sure and also using the homomorphic encryption and AEC encryption. So like, as you know, like my main research part is to work on the agricultural side. In agriculture, the farming industries, they don't have the enough resources. They are using the low IoT devices and they don't have a powerful resources like the fintech or health tech have. So based on these privacy top techniques like the homomorphic encryption, SMPC, and the differential privacy, and we are using the federated learning. So what do you think about like for the low level devices like Raspberry Pi, like they have the 500 MB of RAM, and these techniques needs a lot of computationals to do more encryption to secure the data. So what do you think about this? Like for the low level of devices, which technique is more better for this? Right now for my research paper, I use the homomorphic and the AES encryption using the federated learning. But what's your suggestion on this? Yeah.
Let's find out.
Yeah, thanks a lot for the question. So, of course, when you look at low resource end devices, you also need to cut down on what you can do with your machine learning, right? So you need to use maybe the tiny machine learning Python library, that kind of stuff. And but to go beyond that with privacy, then what you would like to see is maybe a very simple ways of aggregating. Like when we work with gradients, it's really just adding things together. So if you can quantize your model parameters quite dramatically, right? So it's robust against like that type of quantization. You may be able to really in practice bring down, say, the circuit complexity or the way you do it. But you can do this. Hey, you can do the arithmetic type of encryption, circuitry evaluation. But with just homomorphic encryption, you would like to work with additions. But you need to map this also in the in the right domain, right? So you need to think about all these aspects. Now the nice thing with but you have a lot of constraints. I can see that. So it's a give and take. In practice, that's what you do. You want to see maybe I will use the secret sharing approach. That makes total sense because it's a very cheap technique. So I have a few servers that do not collude together and that will run an MPC protocol among themselves because they do have the computing power. So that is probably what I would do. I would do the secret sharing, because I mean you cannot even have a full-fledged operating system on your device, right? So you have a real-time operating system, which is pretty basic. So yeah.
Thanks so much. I have a question from an online viewer, Betul. Privacy is one of the most debated issues in the development of the Internet of Behavior technology, a new technology that utilizes machine learning and deep learning techniques, particularly behavioral data. While cloud computing technology is so advanced, it has both positive and negative impacts. I'd like you to comment about this issue.
Um, hmm. So, so the So what I hear is that with the new data that is being used for learning machine learning models, we have like the new data representing behaviors. What can we do there? Yeah, I personally, it's really about from academic perspective, you will use the same type of techniques as always. That's for sure. Like everything that we talk about here. But if you want to go into a practical application, you want to understand the data, just like what we saw yesterday, the process mining. You want to understand the data. You want to understand what you need to keep private, right? So if you represent it in a feature factor, what is it that you really care about? So if you start to get an understanding about that, then you can have different privacy guarantees for different components. So you can do that as well. So that's the type of question you will have to ask yourself. And it needs to be practical if you want to have output right now. So you cannot go all the way, right? You cannot apply, I mean, as I demonstrated, we're still busy with the transition to practice to these very high level IDs. And you need to taper them down in the right way.